Think of a manufacturing process like trying to park a car. The width of the car represents the natural variation of your process. The painted lines, or the garage walls, represent your upper and lower specification limits. Process capability is the mathematical measurement of how well that car fits into the garage. It evaluates your process's ability to consistently produce output that meets the design specifications. Before you can run any capability math, two conditions must be strictly met. First, the output must follow a normal distribution. Second, the process must be in a state of statistical control. If special causes of variation are active, your capability calculations will be completely invalid. Stability comes first. It is entirely possible for a process to be in control, but not capable. You might have a highly predictable, tight bell curve of data, but if it falls completely outside your specification limits, you are reliably producing defective parts. To gather the data for these evaluations, we run three main types of studies: a peak performance study for ideal conditions, a process characterization study for actual operating conditions, and a component variability study to isolate specific sources of variation. In short, stability tells us if a process is predictable. Capability tells us if that predictable process is actually useful to the customer. We quantify this potential using the Process Capability Index, or CP. The formula divides the entire specification range, the upper limit minus the lower limit, by the natural variation of the process, which is 6 standard deviations. This graphic illustrates 3 capability scenarios. In the top panel, we see a CP greater than 1. The natural spread of the process fits entirely inside the tolerance limits, with room to spare. In the middle panel, CP equals exactly 1, perfectly matching the tolerance. In the bottom panel, CP is less than 1. The variation is wider than the allowed tolerance, guaranteeing a large number of defects. However, CP has a major blind spot. It only measures the potential width of the process, because it strictly assumes the process average is perfectly centered between the limits. This chart shows exactly why that is dangerous. As we scan down these panels, the bell curve drifts further and further off-center. Yet the CP value remains firmly at 2.0. The process is producing non-conforming parts, but CP ignores the shift entirely. To find the actual capability, we must calculate two one-sided ratios, CPU and CPL. These calculate the distance from the actual process mean to the upper limit and then to the lower limit. By taking the minimum value, CPK reveals the worst-case performance, showing how dangerously close the mean is to a boundary. Notice how CPK plummets to -0.5 as the process crosses the upper limit. This excerpt shows example 8.11 from the text. We have a target specification range from 10.55 to 10.90. We've sampled a process with a mean of 10.7171 and a standard deviation of 0.0868. Take a moment to calculate the potential capability, CP, and the actual capability, CPK. Calculating the one-sided limits reveals a CPU of 0.70 and a CPL of 0.64. Taking the minimum yields a final CPK value of 0.64. While CP suggested the process had potential, CPK proves the actual performance is failing because it punishes the process for being off-target. To quickly quantify exactly how far off-target a process is, we use the K-value formula. This calculates a scaled distance from 0 to 1, where 0 is perfectly centered, and 1 means the mean has shifted completely onto a specification limit. Because of this, CPK and CP are mathematically linked. CPK equals CP times 1 minus K. This proves that actual capability and potential capability are only identical when the process is perfectly centered and K is exactly 0. So, what number should you aim for? Industry minimum standards dictate a CPK of 1.33 for existing processes. For standard new processes, the baseline increases to 1.5. If the new process involves safety, strength, or critical parameters, the requirement is a strict 1.67. These are the rules. Ensure strict statistical control first. Measure potential capability with CP. Evaluate actual off-center performance with CPK. Mastering these indices gives you the statistical evidence required to prove your quality to consumers and allows you to prioritize exactly which processes need engineering intervention first.